Let's briefly review factoring. So we already said in the last video that if you have an nth degree polynomial, it can be factored in general into n linear terms. But that's only true if you allow all of the roots to be complex values. And in this class, we're not. We're only factoring over the real numbers, which means that you might have an example of a polynomial which it's not possible to factor all the way down into linear factors. So for example, this equation, even though you see it's a fourth degree polynomial, is really sort of like a quadratic in disguise. So if we call p a new variable, x squared, you can rewrite this equation as p squared plus 4p plus 3. Because you see that we only have even exponents here, and so you can rewrite it as a quadratic in x squared, as we say. So you can use the factoring techniques you already know to factor this one quite easily. So I need two numbers that multiply to be 3 and adds to be 4, and clearly 1 and 3 do the trick. And then we can substitute back in for p, and that gives us that our original equation factors as x squared plus 1 and x squared plus 3. And each of these terms is a quadratic, so you might imagine that you could take that term and factor it into 2, and take this term and factor it into 2. But you'll also notice that if you imagine the graph of x squared plus 1, for example, it's an upshifted parabola, and so it has no roots. And that's just another way of saying that it has no real factors. So each of these is prime if you're factoring over the real numbers. So that was an example of a fourth degree polynomial where you're only able to factor it into two prime quadratic factors. You also learned an important factoring technique that maybe you didn't know already, which is paying attention to see whether your higher degree polynomial is actually secretly a lower degree polynomial. Go ahead and try the technique on your own. Let's say I gave you x to the fourth minus 9x squared plus 20. Try and factor it as far as you can. Pause the video, give it a shot. Okay, so applying the same technique here, I'll call p x squared. That lets me rewrite this equation as p squared minus 9p plus 20. So here I know I need two numbers that multiply to be 20, but add to be negative 9. I know that 5 times 4 is 20, and 5 plus 4 is 9. So let's think here. So if they're both negative, then when they multiply, you'll get positive 20, but when you add, you'll get negative 9. Except we're not working with x anymore. This is p and p. So we've successfully factored this, and now we can rewrite back up here, but substituting back in x. So we've got x squared minus 4 and x squared minus 5. But I hope you didn't stop there, because you always want to think about what you're doing. And in this case, there's a really important difference between this answer and our previous one. In our previous one, each of these quadratic factors was prime because they couldn't be factored any further. In our case here, neither of them are prime. You can factor both of those. So x squared minus 4 is what's called a difference of squares. So that factors as x plus 2 and x minus 2. The idea of the difference of squares is if you have a number that's a square number minus another number that's a square number, you can always break it apart as the square root of the first plus the square root of the second times the square root of the first minus the square root of the second. And the reason that makes sense is because you have this pattern where you're going to get triangle squared when you do that. When you multiply here, you're going to get negative triangle circle, but then here you're immediately going to get positive triangle circle, and so those subtract to be 0. Those cancel each other out. And then here you've got circle times negative circle gives you negative circle squared. So you can kind of see how that pattern leads to a cancellation of what would usually be the term in the middle, and you're left over with only the triangle squared and the circle squared. So maybe you wrote this far, but you should realize that this can also be factored. Just because 5 isn't a perfect square number doesn't mean you can't still apply the difference of squares. So consider x plus root 5 times x minus root 5. Now imagine multiplying this out. We'll have x times x as x squared, then we'll have minus root 5x, and then we'll have plus root 5x. And so those cancel each other. And then we'll have minus root 5 times itself, which is minus 5. And that's what we started with. So the pattern for the difference of squares you can apply even to numbers that are not square numbers. If you wanted to think about this differently, remember that whenever you're finding factors, really you're finding roots. You're finding solutions to the equation when you set it equal to 0. So perhaps a different way of thinking about it would be, let's figure out what is this equal to when, what could x be equal to when it equals 0. And so that means x squared is 5, which means x is plus or minus root 5. And that gives us the two roots. And then you know that you can rewrite it in root form, where you've got x plus the root and x minus the root. So that's sort of another path to the same factorization. So I hope that that is what you ended with as your final answer. Think about this one for a minute. So it's a fourth degree equation, but unlike the previous examples, we can't set p equal to x squared and rewrite it, because the problem is this fourth degree term would be p squared. This would just be p, but this you couldn't rewrite this as an integer power of p. So that doesn't let us rewrite, so making a substitution here doesn't let us rewrite it more easily. However, hopefully what you do notice is that all three terms have some factors in common. In particular, x squared is in all three terms. And it looks like 2 is also a power of all three terms, or a factor of all three terms. So let's take out 2x squared from all three terms. And that gives us 5x squared minus 9x minus 2. So now we've got one factor, and now we've got another that we could potentially factor ourselves. So this one's maybe harder than some of the previous examples because we don't have a leading coefficient that's 1. However, there aren't a lot of 5 is prime, so there aren't a lot of ways to divide it up into pieces. So we know that one of these terms has to be 5x and the other has to be x, because there's no other way to do it. If this was 6x squared, then one could be 6x and one could be x, or one could be 2x and one could be 3x. But in this case, there's only one way to divide them up. So now that we've divided them up this way, we're looking for two numbers that multiply to be negative 2. But those same two numbers, 5 times this number plus that number, has to equal negative 9. So let's start by thinking about what these two on the outside might be so that they could multiply to be negative 2. So the only two possibilities are really 2 and negative 1, negative 2 and positive 1. What am I missing? Negative 1, positive 2, or 1, negative 2. Does that make sense? Right, because I know one of those has to be negative so that the multiplication ends up negative. And I just wrote out all the possibilities. And the reason that 2 and negative 1 isn't the same thing as negative 1 and 2, the reason the order matters, is because remember, when you multiply it out, this number is going to get multiplied by 5, but that number isn't. So let's see, just scanning down and thinking about it, it sort of makes sense that 5x times negative 2, that's negative 10. And then if I just add 1, that gets me negative 9. So I think this bottom one is the one that works. So this factors as plus 1, negative 2. And now I have factored it out into 4 linear factors. So to review, you saw 3 different patterns, or things that I think you've seen them all before. You could factor out all the common factors to all your terms. You could rewrite your equation using a substitution that would let you reduce the overall degree, and we did that when we substituted p for x squared. And then there's the difference of squares pattern. So because the factors of a polynomial are the building blocks, they're what you use to understand the behavior of higher degree polynomials. If you can figure out the pieces that they're built out of, you can start to make sense out of more complicated functions if you understand the pieces that build them up. So I hope you enjoyed this quick review. Good luck on the problem set.